Hi folks, welcome to lecture 8, and in this lecture we'll be analyzing cubic functions. So just to see where we are in the grand scheme of things, we're looking at cubic functions. These are the other functions then we'll be tackling towards later on, and then we'll be determining the nature of functions and taking a look at calculus as well. So cubic functions, simplest equation. We looked at some of these in the previous lecture, just as a quick overview. Typical graph, or if it's a simple function, curve looks more like that. Yeah, it's that kind of a that's not great actually. No, that's not right, sorry. I have to be fussy about these things because that's more what it's like. Sorry, just to be correct. So one input, one output, as we said, continuous. Highest power is x to the power 3. And just a few examples, volumes, particularly of simple shapes, cubes and spheres. Wind power, here's the cubic element. And then the power used by pumps and fans. Also there's a cubic relationship between power and the speed of the pump or fan. So we take a look at an example with a simple cube. So each side is 10 centimeters. So if we wanted to work out its volume is 1,000 centimeters cubed, 10 by 10 by 10. But now determine the change in volume when the length of each side is first of all increased by 20%. So here we're just taking a look at, well, what's the change? So it's new over old. We get this ratio of new versus old. That's also called a ratio when you're comparing exactly this, a new value to an old value as a fraction. So if each side is increased by 20%, 20%, 1/5 of 10 is 2, etc., etc. Each side is now 12. And when we compute this with your calculator, you could do a little bit of cancelling if you wanted, but most people will go for their calculator. We'd see that the volume increases, so your answer will be 1.728, or sorry, because it's percentages, it'll be 172.8. So just be careful in the question. It will usually ask for the percentage increase or percentage decrease in volume. So that's what we're looking for. The original 100% plus this increase. So just be careful of that with the question. Sometimes people get cut out and they enter in 172.8. That's not the increase. That's the new volume as a percentage. So just be careful of that. Now part B, what happens if it's halved, if the sides are halved? So now it's still volume of the new one, volume of the old, 5 cubed over 10 cubed. And now the volume is decreased by 87.5. So when you actually work this out, what you'll get is 12.5%. So this cube is only 12.5% of that cube there, which was 100%. So the decrease is simply this minus that, which gives us a decrease of 87.5. So again, just be careful I think I have a question like this just on the next slide. So just be careful you don't get caught out when you're entering your answers. So here's a similar type problem. So first of all, find out what's the percentage change in volume when the radius of a sphere is increased by 10% and then decreased by 30%. So same idea, just use your percentages, new versus old, because it's been cubed. I'll just talk about this a little bit, just to be careful. Here we're going to have V is equal to 4 over 3 pi, so whatever this is, it'll be volumes actually, so I don't need that formula. So the new volume is 110% to be cubed over 100 to be cubed. Now you can always do a little bit of maths here as well. This is going to be 110 over 100 to be cubed. Divide top and bottom by 10, or even just do the maths and it'll be 1.1 to be cubed, and then multiply that by 100. So that'll get you there. So we'll see this again and again, guys. The maths is actually often a lot more simple than it looks. So I'll let you work through those first of all, and then as we progress. Good idea to try them now, guys, and then hopefully when you move further into the video, I'll show you a few little tips and tricks that'll kind of simplify the process and kind of make the maths quite easy. That once you get in the pattern of what's going on, you'll be able to kind of bang through the problems fairly quickly. So here we have a small orange, and that has 36 calories. So I kind of did a little bit of research, so I think that's about right. Now, how many calories would be in an orange 8 centimeters in diameter? So this is where people kind of intuitively apply linear reasoning in inappropriate places. So a lot of people here think, well, it's only increased by a third, plus 2 centimeters in diameter. That's 1/3 of this. So a lot of people would be thinking maybe about 48 calories for the bigger orange, which it'd be kind of logical, but unfortunately it's very incorrect. So we'll take a look. So the volume of a sphere is given by this. What we want to do is compare the new volume to the old volume, and then multiply it by the old calories. So this is the crucial bit here. So we want to put in, first of all, the radius. Well, the radius will be 3, and that's what will go in for the old volume. And then the radius here is 4, and that'll go in for the new volume. Sorry, wrong place. But the thing is, you don't have to dive for the calculator. Well, you will, but without typing in everything, I hope you can see there's lots of easy cancellation. And like I said then on the previous slides, is really the maths becomes down to new over old radius, diameter. It would be the same if we did, I don't know why it does that. It would be the same if we did 8 over 6 and cube that. If we just kept the diameters, it would still be the same value. So really all you need to do is get the new value over the old value. Because it's a cubic relationship, sorry, that shouldn't be 100, it should be 36. Because it's a cubic relationship, we just have to cube that, the 4 over 3, and then multiply it by 36. So volume, the fact that we're looking at volume is what determines we're cubing everything. And when you work that out, the bigger orange is actually way more than like 2 and a bit times the calories of this one. So that's just something, again, intuitively for people who are kind of trying to lose weight or from a nutritional point of view. Just choosing smaller items all the time will actually lead to a significant kind of reduction in calorie intake. So here's one for you to try. I'm trying to make the potatoes as round as possible, but the principle would still apply if the potato was oval shaped. The maths would be a lot more complicated because we'd be dealing with ellipses and stuff like that. So just imagine these are nice round potatoes. So a small round potato has a diameter of 5 centimeters. A larger round potato has a diameter of 6. What's the increase in calories? Or, sorry, it's not. Sorry, how many calories would be in the bigger one? So this one is 60 calories. And then the question is, how many calories is in this one? So it's still just new volume over old volume, but just remember to cancel. So it's really just new value over old value. We're looking at volume, so things are cubed, and then multiply that by 60. So that's what I'm really trying to teach you guys. That's the maths, and that'll get you the answer. We don't need all this 4 over 3 pi because they're going to cancel out top and bottom. Here's another one, same idea. I'll just let you, I won't explain this, but same thing, only this time we're talking about serving sizes. This size watermelon will give out 15 servings at a restaurant. So how many servings would we get from this size watermelon, 40 centimeter diameter? So exact same process. And again, you'll kind of just be surprised at how a small increase in diameter has a huge kind of change in the quantities involved. This is because we're dealing with cubic relationships. So, wind power is governed by this equation here. So the big P here stands for the power. This is the power available to a turbine. And then we have rho is the air density, A is the swept area of the turbine. And that's determined obviously by the blade length. The longer the blades, the greater the swept area. And V then is the wind speed. And V is the most important element in the function because that's the one with the cube on it. So it's kind of the most powerful. That variable has the greatest influence because it has the highest power. So the small changes in this variable will have big impacts on the overall power available. So we're just going to do a little bit of maths. Rho, air density. I know you'll all remember rho from your Greek letters. A, like I said, the swept area. And V is the wind speed. So we're just going to take a look at A. A is the area of a disk. And the area of a disk is pi r squared. So in terms of our wind turbine, the blade length is just r. And we're going to insert this now, substitute it in here instead of A. So now we've replaced A with pi r squared. And now, just to be polite, we always write any constants at the start. So the half is a constant and the pi is a constant. So to be written properly, our function would now be written like this. And in America, this function is in the wind power industry. In America, this is often called the 1, 2, 3 power equation because the power on density is 1. That means there's a linear relationship between power and the density of the air. Sorry, I hope I clarified that. Yeah, air density. There's a quadratic relationship between the blade length and the power. Remember, R is the blade length. And there's this cubic relationship between the wind speed and the power. So just to write all of that down. Linear relationship with air density, quadratic relationship with blade length, and cubic relationship with wind speed. So now, what I'm going to do is examine each of these scenarios individually. So I'm going to change one element. In the first one, I'm going to just change the air density, but keep the blade length and the wind speed the same. And we'll see how much a change makes a difference. So here's our function from before. And here I have a wind speed of 10 meters per second, a radius, a blade length of 10 meters, and an air density of 1. Now I simplified the air density a little bit just because it's close enough to 1 in real life. So when I do the maths, just feed these values into this function, I get 157 kilowatts. So now what I'm going to do is I'm going to double the air density. Now in the real world, you can't double air density. There's, the air density is what it is. It changes a little bit as you go up mountains. It gets less dense. But other than that, there's very little we can do to change air density. But we're just looking at the theoretical scenario. So in this scenario, the wind speed is the same. The turbine is the same. But the density is doubled. So we're simply doubling this value here. So when we feed the values in, we're putting in a 2 now, where we did have a 1, and everything else is the same. And as to be expected, the power has doubled. So if we double the air density, that doubles the power, because there's a linear relationship between power and density. So from the first set of lectures, in a linear function, if the input is doubled, the output is doubled. In the next scenario, we're going to change the blade length. We're going to change R, which has a quadratic relationship with power. So the blade length and power have a quadratic relationship. Same equation. So the first scenario is the same as it was on the previous slide, but now I'm going to make the turbine bigger. So I've doubled the radius. When we put this through now, we've 20 meters instead of 10. But now we can see there's 4 times the power being generated, and that's because of this quadratic relationship here. In a quadratic function, if the input is doubled, the output is quadrupled. So we doubled the blade length, which was governed by this quadratic relationship here. In the final scenario now, we're going to take a look at what happens if we double the wind speed. Now this is achieved easily enough by simply moving to the top of a hill. So when the wind speed is coming in, the wind would come in, and as they say, it starts to feel the hill. So this is what happens to the streamlines. And then as you get up closer and closer, the hill is less of a bump. So at the top of the hill, there's much more air. The same quantity of air passing through a much smaller space. So there the wind speed increases, and it's often called the doubling effect if the shape of the hill is correct, which pretty much as I've drawn it there. So now we're going to move our turbine. This is the initial scenario, same as the last 2 scenarios. But now I move the turbine to the top of the hill, which doubles the wind speed, as I said. When we feed these values into the function, we can now see here we're actually achieving 8 times the power. So the power available to the turbine here is 8 times what it is here. So this one is 8 times what this one is. So from a revenue point of view, It pretty much costs the same to put up the turbine in either location. There might be a difference of a couple of 50, 60, 100,000, which in terms of wind turbines is small change. But for that movement of the turbine, you're going to generate 8 times the revenue. Just to bring things back a little bit, say if the planners didn't like your turbine at the top of the hill and told you to move it here. Now down here, just in the lee of the hill, in the bottom 1/3 of the hill, here, remember when I drew the speed lines, is the wind actually feels the hill and tends to kind of rise up above it. So down here often the wind speed is halved. That's meant to be a 5 there, not a 6. In this case, if you feed 0.5 in there, you'll find you only get 1/8 of this amount, which is about 20 kilowatts. So the difference between having your wind turbine here on the hill and here on the hill is a factor of 64. And this is why often if planners move a turbine low enough on the hill, then the developers will just walk away from the project because it's no longer feasible. And that's all governed by this function here. So in a cubic function, if the input is doubled, the output is increased by a factor of 8. So it's very important to realize these relationships. And what I'm really hoping is that when you look at a function and you see something being cubed, something kicks in your memory and you kind of go, oh, a small change to this is going to have a big change to my output. Take a look, just an example now. Very similar to the examples we were doing with the oranges and the watermelons and stuff. The function looks a bit more complex, but essentially in both scenarios these values won't change. So we're told at a wind farm, one turbine A has an average wind speed of 6.6 meters per second, and the turbine B has an average, because of topography effects and stuff like this. So the question then, determine the percentage increase in power generated by turbine B with respect to turbine A. So we're comparing B to A. So we're looking for this, the power of B over the power of A. From A, I should say. When we feed everything in, we don't have any values for air density and radius, but we don't need them because they'll actually cancel out. So now again, we're really just back in that scenario of new over old, because we're looking at wind power in relation to speed. That's a cubic relationship. And that's the maths then. When we work that out, we'll find, even though it seems like a small increase in wind speed, the revenue generated by turbine B would nearly be 30% greater than the revenue generated by turbine A. The one thing though, all the time, the main thing is to try and take this thing, is that once you understand it's a cubic relationship, then you can just dive straight into this new over old to be cubed, multiply by 100, multiply by whatever we're looking for, if it's percentages, calories, whatever. And then the answer will drop out quite easily. Here's just one for you guys to try. Exact identical scenario. Just different wind speeds now. So you guys can take it from there then. Now we'll just take a look. This is the last bit, so there's a bit in this, but we're nearly there. So approximately 20% of the total energy consumed on the planet by humans is by pumps or fans. Pumps are used to move water or liquid, and fans are used to move air. So there is a typical pump on the left, centrifugal pump. They're the most common in industry, take up about 90% of pumps. And an axial centrifugal fan as well. Axial fans they're sometimes called. No, they're not. Sorry, they're centrifugal. Axial are different. So now this is slightly different. In the previous example, we had the power was directly related to three inputs. Half pi rho r squared v cubed, and all these three inputs had an effect on the output, and we looked at the individual effect on each one. Here what we're looking at is that the one input, when we change one input, the speed, it has three effects on three separate outputs. So there's three different outputs affected when we change the speed. The first one is the flow, Q, and that's a linear relationship. If we double the speed of the pump, N, then that doubles the flow. There's a different function though. Another thing changes independently of flow is the pressure in the system. And that's a quadratic relationship. And finally then, I should really write these the other way. Q is proportional to N. P is proportional to N squared. That's a better way of writing them, a bit more mathematically correct. So P is the pressure in the system. And then there's a cubic relationship between the power used by the pump and its speed. That's a N there. So this is a typical pumping system, very simplified. This isn't really, but it's just to show the pressure in the pipe is what P is. So if the speed of the pump, so you would just turn a little dial, double the speed of the motor, and that this is the pump and this is its motor. So you could very easily change the speed of the motor, which changes the speed of the pump. So if we double this, what happens is up here, the flow is doubled. The pressure in the pipe is multiplied by 4. Now, there's another word here, head. Head, guys, if the system is open, then the pressure would stay the same because there's an opening, but the pump would be able to pump to 4 times the head. So if this was this was the limit of the pump at the first speed, when we double the speed, it would now be able to pump to 4 times higher. So head is the idea of, in an open system, how high can you pump the water, and pressure is in a closed system like your radiators, how much pressure would build up in the pipes if I doubled the speed of the pump. So that's just something, when you double the speed, doubles the flow, quadruples the pressure or the head, whichever we're talking about. But the main thing then is the power consumed by the motor increases by a factor of 8. So your electricity bill increases by a factor of 8. So flow is proportional to speed, pressure is proportional to speed squared, and power is proportional to speed cubed. So here we've got the one input, the speed, but you can see there's 3 different graphs. We have a linear graph for flow, we have a quadratic graph for pressure, and we have a cubic graph for power consumed. Just to put this into context, I had a student years ago. I used to teach energy management, and he worked in, I won't give the name, but he worked in a big, huge factory in the Midlands. He went into all the clean rooms, reduced all the speed by, I think it was 10 to 15%, and saved £1 million a month in that company's electricity bill. So Quite a significant savings. Now, unfortunately, the FDA came along and said, no, 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 you're not allowed to do that, and made them turn all the pumps and stuff back up to full speed. All the air changes had to go back up to what they were originally. So there's big money to be made out there, guys, if you can do it within regulations. I could talk about this for a long time, but I better keep going. So with flow, this is the typical equation. So these are known as the affinity equations. We'll work with these a little bit in the next few slides, and then we'll finish up. Pressure and power. So these are the three affinity equations, they're called, the affinity laws. And every engineer kind of knows all about these. What I'm really exploring is the mathematical, the cubic relationships. So we'll take a look at a linear scenario. So a pump speed is reduced by 30%. So we know all the values. So we know what we're trying to feed in here is the new flow, which we don't know. But we do know the old flow. Well, the old flow was 100%. Sorry, these are coming in. The new speed is 70%. We're reducing by 30%. Sorry, I'm putting these, I'll write these in and I'll actually come back and do this one again. 33. Okay, so we'll clear this off. Go back. Okay, so now we're going to take a look at some practical examples of this. So we're first going to take a look at flow. And we're looking at a scenario where a pump speed is reduced by 30%. So the original speed, which we will call N1, is 100%. We're going to reduce by 30%. So the new speed is going to be 70%. So we're going to look at this equation. Now, like I said, we'll be feeding in the new speed, 70, the old speed, 100. Now, the old flow, Q1, was obviously 100%, and we're wondering, well, what's the new flow? So we put all these values in. Now we multiply, well, I'm going to simplify this down to 0.7. And then I'm going to multiply both sides by 100. So when we do this, we get the new flow is 70%. So Q2, I was going to write in new and old, but in nearly every manual you'll come across, it's always Q1 and Q2. So I said I better stick with the proper notation. So 2, guys, represents the new, 1 represents the old in all of these functions. So Q2 is 70. So in other words, when we reduce the speed by 30%, we reduce the flow by 30%. Remember, this is the new flow, so the old flow was 100, so that gives us our 30% decrease. And here we can see, so we've reduced the speed by 30%. Because it's a linear relationship, the flow reduced by 30%. And that's, again, most people's intuitive reactions would be like, yeah, so hot. But it's just the two other parameters. When you change the speed, you change the flow, but automatically the pressure changes, and automatically you cannot stop the other two outputs also changing. So now we look at the pressure. Here we're reducing the pressure by 30%. So this relationship is still the same, 70 over 100. Or in other words, sorry, an extra 0 appeared there unwittingly. Or else we could just say 0.7. I always try and work these out first. Feed in our values, old, 100%, new, 70. Old, 100%, what's the new? Feed it in. This again is 0.7, but now it's been squared, and that's the major difference. Multiply both sides by 100 to get this guy up. And when you work that out, the new pressure is 49. So there was a 51% decrease in pressure when we reduced the speed by 30%. So here we reduced by 30%, but because of the quadratic relationship, we reduced the pressure by 51%. And in lots of systems that mightn't be acceptable, like now the pump can only pump to half the height it could before, which might mean that that speed change isn't viable. But that this is what would happen if you reduce the speed by 30%. So this is what engineers use these to explore, you know, what happens if I do this, what happens if I do that. We're emphasizing on the nature of the relationship, this quadratic relationship, cubic relationship, linear relationship. Now we look at the most important one, where the money lies. We're, again, same scenario, pump speed is reduced by 30%. So we're really asking, well, what's this value, Q kilowatt new? What's my new power requirement going to be? Here again, this is our 0.7 to be cubed, so that's the key. And now, because we're looking at power, it's a cubic relationship. And the new power requirement is 34.3%. So that means the power requirement has reduced by nearly 66%. So we reduced the speed by 30%. As a result, the flow changed by 30%, the pressure changed by 51%, but the power has dropped by nearly 66%. So you're only paying 1/3 of your fuel bill. So often it makes a lot of sense in industry to slow down pumps if it doesn't matter. You know, if you've got 2 days to fill a tank, pump slowly over a long period of time rather than turning on the pump for 3 hours at full blast. You would use a lot more power with the latter scenario, full blast, than you would with the slow, lower pump speed over a longer period of time. So just an example to work out. So centrifugal pump is equipped with a variable speed drive. So this is the old speed. This is the old flow. This is the old pressure. And this is the old power. So now, when the pump speed is reduced to 2,800 RPM, what's the revised flow rate, pressure, and required motor power? So we have to do 3 little sums. We need to use this function, and our power function. You'll be given these in any kind of an exam scenario if you need them. So first thing you do is from the old and the new pump speed is determine this relationship, new speed over old speed, because this is the engine that drives everything. Cancel top and bottom and we get 4/5, which is 0.8. So that's the relationship of this. So now what I'm going to do here, here's my equation. I'm going to multiply both sides by Q2 to bring it up, Q1, sorry, off the bottom. And now it appears here. And now I can just feed in all my values. I'm just going to feed in this relationship though as 0.8 from up here. The old flow was 40. This relationship is 0.8. When I put them in, the new flow is 32 liters per second. So we reduce the speed by 20%. As a result, we reduce the flow by 20%. Now when we look at the pressure, the old pressure was 6. This relationship is still 0.8. The only thing that's changing now really is the squared. When we work this out, the new pressure is 3.8 bar. And finally, we take a look at kilowatts. Again, we multiply both sides by this to bring it up, so we just have the new kilowatts on its own. Feed in our values. The old kilowatts was 26. This relationship, new speed over old speed, is 0.8. Do the maths. Again, what you again notice, guys, again, it's this kind of linear, quadratic, cubic. So by reducing the speed by 20%, we reduce the power requirement by nearly 50%. It was 26, now it's just over 13. So as I said, just small reductions in the speed of a pump or a fan can have huge impacts on the bill, on the electricity bill associated with it. So doing the same type of maths then, I have 2 problems here for you to try, so you can pause the video. So now it was the same system as before, but the pump speed is reduced even further. So what's the new flow rate, the new pressure, and the new required motor power? Here's a problem with different parameters. Again, there's a reduction in speed, and what will be the new flow rate, the new pressure, and the new required motor power. So we'll finish up there, folks. Thanks for kind of bearing with me. There's quite a lot in that, but hopefully you see that once you see that little cubed sitting above one of your inputs, warning bells should definitely ring, that like a little change to that is going to have a big impact on your output. And that's really the essence of this lecture, like that. If the input is doubled, the output is multiplied by a factor of 8. And it's very good to be cognizant of that when you're making changes to a system that's cubic in nature. So we'll finish up there, folks. Thanks again, and we shall chat to you in the next lectures.